Okay. Yep. You're going to tell me when, right? Okay. Well, welcome to the last class, day 13. Today we'll talk about bimodules and data migration, and so hopefully make things more concrete than they have been for a while. So we'll start with databases and duck queries. Duck here means disjoint union of conjunctive queries. So we'll talk about those in concrete detail a little bit. And then we'll talk about how bimodules migrate data from one database to another database by basically taking the database you're going into, and each table in it asks for a query, a duck query on the table you're coming from. So we'll talk about that. And then we'll talk about, then we'll get into abstraction again. I guess we love abstraction. We start and end with it. But we'll talk about the pro-arrow equipment cat-sharp, which includes categories, which are polynomial comonads, cofunctors, which are maps of polynomial comonads, and bimodules, which are data migration functors. So categories, cofunctors, and data migration is this pro-arrow equipment. You don't have to know what a pro-arrow equipment is. I'll like sketch out what it is very briefly. And finally, I'll just put some closing remarks about like how to stay in touch and stuff. Okay, so we'll start with databases and querying them. And a database is the way that computers hold all of the world's information, basically. A database consists of a schema and then data conforming to that schema. What does it mean that it conforms? Well, we'll talk about that. So a schema, so an example of a schema, so a schema is just going to be for us a category. Now, sometimes the category will have a little more structure than it'll be a little more than just a category, but I'll talk about that in a second, or maybe 3 minutes. So here's a little category. It's got two objects, E and V for edge and vertex, and two morphisms other than the identities, source and target. And that's a schema. And data for it will be like a bunch of tables, one for every dot here. So this table will have E as the identity field, so it'll be, maybe I should call this edge or something, edge and vertex. And so you have this edge thing here, and then you have source, and you have target, and you might just write down a bunch of edges, like 1, 2, 3, 4, 5, 6, and a bunch of vertices in another table. And the identity column always has, I always put these two lines to remind you that this is like a special column, and these are like other columns. So vertices, maybe there's A, B, C, D, E, and there's no other columns. And maybe edge 1 goes from A to B, and edge 2 goes from B to A, edge 3 goes from C to D, B to C, and this one goes from B to C again, and this one goes from C to D, and this one, or who knows, and this one goes from D to itself. And I could call this the indexing, or the schema for graphs, because the data here would correspond to a graph. We could draw it as like vertices A, B, C, D, E, I guess. So we have 5 vertices, and we have edge 1, and edge 2, and edge 3, edge 4. Oh, sorry, I should tell you what I'm doing. Edge 1 has source A and target B, so I go like that. Edge 2 has source B and target A, so I draw it like this. And this is just I put it in a thought cloud because we're just drawing this thing. But so we have B to C called number 3, and then B to C again called number 4, edge 4, and then C to D is edge 5, and then D to D, edge 6. And it's okay if we have loops, it's okay if we have multiple edges, it's okay if we have isolated vertices, all that stuff can be in a graph. And the point is that this graph here is a functor from the category graph. So I told you this thing was a category. It's got 2 objects and I guess 4 arrows, but only 2 of them are non-identity arrows. But here's a functor from G to set, and this is the data. So I is called an instance of the schema graph. And it's a functor from graph to set, meaning it assigns to every vertex, every object here, a set. So it assigns to the set, to this object, it assigns the set 1, 2, 3, 4, 5, 6. And it assigns to I of the other object the set A, B, C, D, E. And it assigns to this morphism the function. A function is a morphism in set from edge to vertices that takes every edge to its source, and that's written here. And it assigns to this arrow this function from edges to vertices. And so all the data of a functor is given here. And in general, a database is going to be something like this. So I've written up another example that I've used for a long time. So if you've seen this example before, here it comes again. So this is the schema C. It's a category. And this schema has 2 blue objects here, and then 1 open object that I didn't need here. And so this is the part where you actually put like real world like types in there, like strings. So let's look at this again. We have 2 objects, and those are the 2 tables. And we have all these arrows. And if you look at the arrows coming out of emp, there's manager, so that's here. There's works in, that's here. And there's fname, that's here. And if you look at the arrows coming out of department, there's 2. Admin, that's here. And name, that's here. So the columns on a table are just the arrows out, plus the name of the object itself. And then, so like for works in, it goes from employees to departments. So works in of 1 is I, and that's a department. And works in of 2 is S, and that's a department. So it's like just each one of these columns is a function from the set for this one to the set for this one, or vice versa. Whatever the arrow tells us, that's the direction of the function. And then this special one, string, it's as though we have a gigantic table like the vertex table full of every possible string. But of course, you would never write that. But that's where like number 1 goes to the string way down the list that says Alice. And then number 2 goes to the string even further down the list that says Bob. And so this is like a special table, and we'll get into how you deal with that later. But basically, a functor from this thing to set will assign to every one of these dots a set. Like 1, 2, 3 is assigned to emp, and is, the set is, is assigned to dept. And every column gives you a function. So this is called the schema, and this is called the data or the instance. And it's a functor from the schema to the category of sets. Okay. Now, why that could be interesting for us is that categories equals polynomial comonads. And C sets so it's a polynomial of, remember C was like the polynomial that was like the sum over all the objects of C of y to the C bracket I. That tells us all the objects and all the outgoing morphisms. Epsilon tells us the outgoing morphisms, it's the identity. Delta tells us the way we take codomains and compose. And so polynomial comonads are categories. And the C sets are, as Nelson told you last time, data migration functors from, well, I guess I called it I. So this would be the instance. I often use the words C instance and C set interchangeably. And if you're worried about this string thing, try to ignore it for now. We will get to it when we get to part 3. For right now, we're just going to look at functors to set, because there's already a lot of stuff going on there. And so the point is, polynomial comonads and C-sets are like already occurring in the pro-arrow equipment or in the thing cat sharp that we've been looking at recently with bicomodules and stuff. But one thing you want to do with databases is you want to query them. So querying an instance is like in SQL, which is a common database query language, you would write things like select, select everything, say, from yeah, so we often want to query instances. We use SQL, SQL. Are we good, Nelson? Okay, so we would select from E1, I actually don't know the syntax, E1 as edge maybe, I'm just going to guess here. If it's wrong, I'm sure anyone who knows it will be able to fix this. E2 as edge, where E1.target equals E2.source. And this query will look at our graph and we'll find all pairs of edges, E1 and E2, where the target of E1 is the source of E2. So it will find all paths of length 2. But you could also find paths of length 5 or parallel edges, E1 and E2, where source of E1 equals source of E2 and target of E1 equals target of E2. That would find parallel edges. You can find loops. You can find anything you want. That's called querying. And sometimes you might want to say, so I don't know how they indicate a comment. I don't know, like this. But then you could also say union, select from where some other stuff. And this thing would be called a conjunctive query. And this thing would be called a conjunctive query. And the union here would be called a union of conjunctive queries. Now we're going to talk about disjoint unions of conjunctive queries because we're going to take all the answers from this one and all the answers from this one and just take their disjoint union as the answer to this thing. And so the math certainly does not let you just union things. Like the math does not just union things, it disjoint unions things. That's what we'll be talking about today. If you really, really want to union things, there are ways of doing it using the topo stuff, but like let's ignore that. So the point is, this is a conjunctive query, this is a conjunctive query, this is a disjoint union of conjunctive queries, and that word is so long, disjoint union of conjunctive queries, that I abbreviated it to duck queries, D-U-C queries. So duck queries are like the bread and butter of databases. You can look for all paths of length 1, 2, 3, or 4 in your database, and that would be an example of a duck query. Please give me all paths of any length, or length 1 through 4, or whatever. I guess in SQL, you probably couldn't ask for a path of any length. I don't know. But in polynomial functors, you could ask for a path of any length, which may or may not be implementable. Because, I mean, it's hard to get infinite things on a computer. But anyway, so let's call those duck queries. And here's what I want to say is that so here's a really interesting thing. Conjunctive queries on D, or on C are C-sets. But if you want to talk about morphisms between queries, they go backwards. But anyway, they're basically C-sets. So how is this thing a C-set? So that is for any query Q that takes a C-set, like our path here, our graph here, and returns a set. So this would take like our graph G and send it to all the set of paths of length 2 in G. For any query, there is a unique, up to isomorphism, a unique. People write essentially when they want to say up to isomorphism. There is an essentially unique instance. Up to isomorphism, there's exactly one instance, Q bar in C set, such that Q of I, for any instance, I was the name of our instance, so let's call it that again. I was our graph over here. For any instance, Q of I is HOM in C set from this Q thingy, Q tilde to I. So this thing here is called the frozen instance for Q. Now, when I say it's called that, I think the only person who uses this term is me, Ryan Wisniewski, and someone named Fokion Kalaitis. But he's a very famous database person, so all his students probably know this term. But it's like not in Wikipedia, so it's kind of annoying. But it is called, some people call it the frozen instance. So what's going on? So how is it that this query, this conjunctive query, for any conjunctive query, we're going to get to duck queries in a second. For any conjunctive query, we're supposed to be able to find an instance. So here's a conjunctive query. What instance is it? Well, it's finding all paths of length 2. And like the generic path of length 2 is this thing. In other words, it's like edge, source target, vertex, E1, E2, whatever, V1, target V2, V2, V3. So if you look here, V1, V2, V3, the generic path of length 2 has 3 vertices and 2 edges, and I wrote it down. And up to isomorphism, there's only one of these. And the point is, if you look at all natural transformations from this C set to I, any C set you want, it will pick out, it will have to send this edge to one of these edges, and it'll have to send E2 to another one of these edges. And it doesn't care where it sends the vertices. It just matters that that the target of the E1 is the source of the E2, and so it will find this query. So HOMing this little graph into that graph is the same thing as querying that graph in this way. And so the point is that queries on a database can be given by just frozen instances. And if I give you a map from Q1 to Q2, this tilde does not mean that it's a special kind of instance. It's just an instance. The only reason I'm writing it is because I'm basically saying that there's this thing called querying. And I can query an instance, and I can query an instance with the other one. And that'll give me a map backwards on queries. Why? Because this one is HOM from Q1 to I, and this one is HOM of C sets, all the natural transformations from Q2 to I. And if I have a map from Q1 to Q2 and a map from Q2 to I get a map from Q1 to I. So given one of these guys, I can take a query result and send it to the result, first do F and then the result. Okay, does that make sense? Okay, someone here is nodding yes, so that's pretty much good enough for me. So what I'm saying is conjunctive queries on C are C sets. They have frozen instances, unique, up to isomorphism. So this is like These are equivalent. And morphisms, if I have a morphism of these frozen instances, I get for any I a morphism that way. And this is a natural transformation. So like morphisms of C sets gives you morphisms of queries going the opposite direction. And okay, so that's what a conjunctive query is. And a duck query is a set of conjunctive queries. That'll be added together. And so to give a duck query, all I need to do is give you an element of what's called the coproduct completion of C set op. So duck query on C is the coproduct completion. In other words, a sum of, like a formal sum of C set op. But I think somewhere along the way, we must have said, well, I don't know if we said this or not, but this is exactly the bimodules from C to Y. Like, this is the bimodules from C to Y. Maybe we haven't said this, I'm not sure. But basically, the duck queries are exactly the ways, they're exactly the bimodules from C to Y. And a morphism of bimodules will give you a morphism of duck queries, and vice versa. So this is the thing that I want to explain today. At least, that's the next thing. Let's see. Yeah. So maybe I can explain a little how this goes. If you, what I need you to maybe remember is that one of those days I gave you, last time I talked, I think, I gave this bunch of the following, TFAE, the following are equivalent theorems. And one of them was that C sets is representable right C modules. And what does that mean? That means that if you look at, if you have this C thing, and this thing here is representable, then this thing is a functor from C to set. Okay, so why is that? If you have a bicomodule like this, if this one's representable, then there's really no data on this side. So what's happening is I have this y to the a thing here, and then I have y to the a here, I have c here, and so nothing happens there. And then I take an element in A, and it lands in some spot in C. And then for every outgoing morphism of that thing, I can take A dot F. So in this picture here, I guess, so basically what this A thing will be the category of all the elements. So here you see 5 elements, 1, 2, 3, 4, 5. Then this A will have 5 things in it. And so what will happen is, if we wanted to think of this as a bimodule, you take any one of these 5 elements, and it will land in some object of C. In other words, it'll land either in emp or dept. And again, we're not worrying about string right now. And then, if somebody gives us a morphism out of emp or dept, like works in or manager or admin or whatever, then it will tell us, oh, you want the manager of number 1? That's 3. Oh, you want the works in of number 1? That's I. And so the fact that this thing has to be like coherent with respect to like identities here and composition and stuff like that, where all, you know, those special fancy diagrams happen, those enforce that this really is a functor from C to set. So representable right bimodule, like C modules, are functors from C to set. The only issue is that like it's kind of up. And you might say, oh, I wish it was just C set. But no, don't wish it was C set, because we're getting to queries here. This is all about queries. We're building up to queries, and C set op is the thing we want for queries. And so if this thing wasn't just y to the a, but an arbitrary polynomial, well, guess what? An arbitrary polynomial is the coproduct completion of the representable polynomials. So that's exactly what we said over there. So if we have an arbitrary polynomial from y, p, from y to c, c is a comonoid or a category, then p is the sum over I and p of 1 of y to the p bracket I. And what ends up happening is that this, I think Nelson probably mentioned this last time, is that when you look at bimodules here, or sorry, just C modules, right, C modules, as you like go through the motions of this thing, the I never changes. This is just I many queries. So it's a disjoint union of I many queries. And this p brackets I, as a set, because this thing is just a polynomial, it's just a polynomial in set. As a set, this will be the set of elements, 1, 2, 3, 4, 5. But in fact, this p bracket I has the structure of is actually a functor from C to set. And so this p brackets I is actually a C set. It looks like a set, but it's just this, it's the set of elements of a C set. And you grab that C set by like looking at you know, this kind of row thing here. So it's a bunch of C sets I, and for each one, the elements live here. And you see what the type of that element is here, and you see how morphisms of that out of that type act on it here. But the I stays the same. And so we just get a lot of P of 1 many different C sets, and we add them all together. And so one amazing thing is that this notation not only reminds you, I mean, to me it's amazing, reminds you of the set of elements, so you can kind of count and see 5. But this P brackets I is in C set. And if y to the blank means Hom, remember it always meant y to the a kind of meant Hom from a to blank. In the olden days, like this is a representable functor. Well, now it's Hom in C set from a as a C set to blank. And so the notation just carries through like really well. This Okay, what do you say? Okay, and so the point is, this P brackets I is not just a set, it's the set of elements of a C set, and this notation carries over not only to mean Hom of sets, but also Hom of C sets. So that's really, to me, really, really neat. And by the way, so maybe it's probably not obvious. If you have a duck query P, and then you have a C set is some, or a C instance, I, like a graph or something, is a bicomodule from 0 to C. Then when you compose these, this is perform duck query Q on I. And what you get is you did have a C set, and now you have a set, which is the set of results of your duck query. So that's how you use one of these data migration functors, is you compose with it. And that's mainly the story of how bicomodules are data migration. The only thing left to talk about is like, what if we went from C to D. Oh, I should put a U here for duck, but that's kind of ridiculous. Okay, so all that's going on there is that this Q will be a functor. You will be able to, if you march through this sort of stuff, you'll be able to turn Q into a functor from D to duck queries on C. In other words, mod, I don't know if this will help anyone, mod DC is isomorphic to category maps from D to mod YC. A DC bimodule is a functor from a regular old functor, not a cofunctor, nothing weird, not a parametric right adjoint, just a regular old functor from D as a category. I guess I was writing it D. From D as a category to regular old duck queries. Did I say this? Duck query. From C to Y. Okay. Let's just see if we can see it. The i's here, the elements of P of 1, are going to be the queries, are going to be all the sum ends. In other words, each I here is going to correspond to a conjunctive query. And we're just saying every query is landing in some C, and given a morphism out of it, we get another query. And that's how it's a functor. Like we're going to just add up all the i's that map to this object of C, and this is going to tell us that that's functorial. Okay. So let me give an example of this. Namely the path monad on graph. So a monad is a functor with some extra stuff, like a bind and a return, or a unit and a multiplication, or however you like to think of it. And I'm going to tell you a monad, but I'm only going to tell you its carrier. Meaning I'm not going to tell you the bind and return. You'll have to figure them out for yourself. Wait. No, I am going to kind of tell you the join. Okay, so remember graph is this schema here, this category. Edge, vertex. In other words, it's the polynomial y squared plus y, because this thing has 3 outgoing and this thing has 1. Plus the comonad things, epsilon and delta, that tell you how to compose. And so the path monad, well, I've actually written this up, so I might as well put it up. Oops. Maybe I'll just put it here. Okay, so graph is this, y cubed plus y, EV thing. And path is a data migration functor from graph to graph. And what is path? It's a polynomial equipped with some lambda and some rho thing, like on that page below there. And so what polynomial is it? It's y plus the sum over n in n of y to the 2n plus 1. You might need to zoom in to see it. I don't know. Okay. Why is it this thing? It's this. So I've kind of drawn a picture. So look at this. And then so this is a map from graph to graph, a data migration functor that takes any graph and gives you a new graph. And if I do that data migration functor twice and compose, that's this symbol. So this and this are exactly the same picture, and we'll zoom in on it in a second. Then the join of the monad is a way to take this thing to itself. And so what is path? Well, I can tell you the underlying polynomial, it's this thing. But I can also draw a picture of it. So a bimodule a CD bimodule will start out with a functor from this thing to set. In fact, from this thing to poly. And then those polys kind of turn into whole duck queries. So this is a picture of the graph for this query. And it's got a vertex, and it's got an edge and another edge, like an edge for 0, edge for 1, edge for 2, edge for 3. And then there's a dot, 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 as though like these are all the rest of them. And so this and this are exactly the same as this, so just zoom in on that. So what goes on for each of these edges? Well, this vertex has the polynomial, corresponds to y. And these edges correspond to the polynomials y to the 1, y to the 3, y to the 5, y to the 7, dot, dot, dot. Now, why would this, if you look at this, I drew a little dot there, and that is a graph. And here I drew an arrow, and that's a graph. And here I do two composite arrows, and that's a graph. And here I do 3 composite arrows. And why would this correspond to the number 1? This one arrow correspond to the number 3. This correspond to the number 5, etc. Well, the reason is because this set here, the exponent, 1, 3, 5, 7, etc., is always the number of elements of the query. And so this query has one vertex in it, has one element. This one has 2 vertices and an edge, that's 3 elements. This one has 3 vertices and 2 edges, that's 5 elements, etc. So this number corresponds to the number of elements you can actually read off there. So it's like the notation really helps you. And even though you probably would need to stare at this for a while to understand how this is a picture of path, path is a data migration functor that takes any graph and returns a new graph, namely the graph of whose vertices are the original vertices, but whose edges in the new graph, which are the union over all of these things of, like the union over all natural numbers of a path of length n. And this says we could compose 2 of these, and if you compose it, it will say, okay, take a path of length 2 in this. So you go, all right, 2, 7. And it says, aha, then I need to be able to give you some concatenated thing, which is a path, namely 9. So this will just take, if this was like 3, I want a path of length 3. All right, 3, 4, 4. Okay, I need to give you 11 here. That's what concat is going to do. And concat, together with like the one that picks out the identity edge thing, the edge, which will be the return or the unit of the monad, is a monad in this category of bicomodules. It's like this kind of thing. And a category C, a regular old category, although we do say that categories are comonads, we can also find categories in this world as the graphs that are algebras for this monad. They're a graph, so a functor from 0, a bimodule from 0 to graph, together with a map like this. That's just an example of what you can do with this sort of thing. Any questions about this? And the nice thing is if you like categories and functors instead of categories and cofunctors, then it really is the category of, like, the algebras of the path thingy here really are the categories and the functors. So we finally, for a long time I was like, how do I find functors inside of Poly? If Poly is supposed to be like my beloved, my favorite thing or whatever, then why can't I find functors in it? And so this is like the first time I found functors living inside of this. Categories and functors are exactly the algebras and maps of algebras for this monad there. Okay. Now, coalgebras are what we usually look at in this course because we were looking at dynamical systems. Coalgebras on path would be pretty weird things. They would basically be graphs, a coalgebra, a path coalgebra. Well, I'll just write the word. Well, what is it? Is it'd be, you have graph, and you have path, and then you have some special graph, G, or not special, it's your dynamical system. And you have G again, and you have a map. So what it would say is, you have all these vertices and edges and blah, blah, blah. And for every vertex or edge, every element of your graph, this map phi will pick out some path in your graph. That's like the next step. So it's like, I'm at an edge, and then like, oh, now I'm going to 53 edges in a row. And you pick out like, which of the 53 edges or vertices do you want to look at? And then it's like a pretty, like, this is a pretty weird example to look at for coalgebras. But in general, what a coalgebra is pretty weird. Like I can't, in the sense that I can't really imagine why you'd ever want to look at that. But in general, a coalgebra you could always, if you wanted to, like, this won't make sense until we get to the equipment stuff. But, I mean, it won't make great sense. But if you wanted to, you could kind of just like erase this stuff and think of it as a regular old dynamical system. So you have a regular old dynamical system, x mapping to p of x. And that's just a dynamical system as we've always known them from the beginning of the course. X mapping to p of x. So a regular old polynomial from the beginning of the course is like a YY bimodule. And you can always take any CD bimodule and turn it into a YY bimodule with the exact same polynomial as you had before. It's just that it no longer remembers how it's related to C and D. And so given any dynamical system, any coalgebra of one of these data migration-y things, we could just look at it as a regular old dynamical system. The difference is that every element of x is now in some table of your ontology. So a CC dynamical system or coalgebra is like an ontologized, and I'm making that word up, but if you've heard of an ontology in like computer science, that's what I'm trying to get at here. It's that every state is living in some table, and like it is like some. It points to some position in this bimodule. It points to some disjunct in your disjoint union of conjunctive queries. And then the directions there are like, oh, which part of this disjunct do you want? Do you want the first edge in your gigantic path or the second edge in your gigantic path or what? And it just kind of like, it just tracks for you what the Hello, testing. Okay, sorry for the audio, guys. So anyway, it just tracks for you. Every state lives in some page or something. Like you have some user interface with all these different like parts to it, and for every state of your system, when you view it, you don't just view it. It's viewed in some part, in some type in your schema or in your ontology, and then like the way it can get updated. And how you get new types and stuff, like states in new tables, is completely schematized by P. So it just kind of does more control on how the dynamical system can update. Like you know that certain states are people and certain states are cats and blah, 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 and that a cat can only become a lion or a person can only become an angel or whatever happens. But like you've got an ontology for how the states are updating. Okay. I wish I had like a nice, concrete, small pedagogical example, but I don't. So the last thing I was going to talk about is the pro-arrow equipment cat sharp. And I think I spent more time trying to be concrete, and I think it was probably worthwhile. But I'll just quickly say something about the pro-arrow equipment. Pro-arrow equipment is also called framed by category. And Mike Schulman's paper on framed by categories is a really nice reference. And a framed by category, or pro-arrow equipment, is a double category, meaning it's got objects like C and D. It's got vertical morphisms like cofunctors. So I'm kind of skipping between the difference between an arbitrary equipment and our equipment. So it's got objects like categories. It's got vertical morphisms like cofunctors. And it's got horizontal morphisms such as bimodules. Oh, and it's got what are called two cells, like maps of bimodules, and or bicomodules. And not only that, this is called a double category if you had all the stuff I've said so far. What makes an equipment or a framed by category is that if the following are equivalent, E1, whenever you have this data, for all this, there exists a universal filler. So I don't know, this is phi and psi and p prime, and here's phi and p prime and psi. There's a universal p and a universal chi or whatever, making this commute, or like there's universal horizontal and two cell. That's number one. Number two is exactly the same story, except I know this one instead. For all this, there exists a this. Exists a universal filler on the bottom. And number three is that for all, like what we're calling cofunctors, but the vertical, there exists an adjoint pair So for every phi here, there's what's called a companion and a conjoint that are adjoint to each other. And well, if I had a map from P to C compose P and from P to P compose D, and someone gave me a cofunctor from C to C prime, well, I could compose with that profunctor. And because of the fact that it's commutative, or sorry, all the little facts about what cofunctors have to do, the rules of bimodules for this will turn into rules for bimodules for this. And so that's how I know that 2 holds. 2 holds. I mean, we have to check that it's universal, but it's not too hard. So what I'm saying is if I had a bicomodule like this, P, I really can't, and I have these two phi and psi things, then I really can find a bicomodule at the bottom too. And in fact, it has exactly the same polynomial carrier. And so this thing forms an equipment, and to finally fulfill a promise from way before, what we're going to do is we have a category C, and there's always a cofunctor to its objects. So this is the discrete category C of 1, Y, Y means every object only has the identity morphism. This cofunctor, there's a unique one that's identity on objects. And then if I had types, and I had my instance, then this chi thing or whatever is the way I assign each of these rows its type. So in our case, maybe we had like, oh, I don't even know what we had. We had some gigantic, let's just say do I have time? Let's just say we had edges and vertices, and every vertex gets a string, and every edge gets an integer for its weight or something like that. Then what I'll do is I'll call this thing C. So we have C, and we have some instance, but let's forget about that for now. We have C of 1y, which is basically 2y. And we have a map from 0 to that, which is string plus string, int plus string. How do I know that int plus string really is a functor or a 2y instance? Well, int will be going to E, and string will be going to V under the lambda here. And when I do this thing, it'll just say I have an instance. And when I take that instance, which has a bunch of edges and a bunch of vertices, and I forget all about source and target, then there will be a map from the edges to int, and there'll be a map from the vertices to string. And so once you do this, and you use the fact that, like, I don't know, all the C mod D things are closed under limits, like they're closed under coproducts and limits, but all I need is limits right now. You can get the queries you want, where you're actually querying for edges with weight 5 or whatever, or employees whose admin person is named Carol or whatever. So that's basically the story of 1, 2, 3. And that's about as far as I can get to today. But for closing remarks, first of all, let us know if you're interested in coding any of this. We would love software projects, or even like Idris or Agda or Haskell implementations of this stuff. Any amount of this, like dynamical systems and wiring diagrams. If someone made some kind of like semograms or whatever sort of picture-y, language-y thing for, putting together like a div mod thing that, calculates 1/7, like in the book, or calculates Fibonacci, or you want to do anything else, the data migration story, any of this, please let us know. We'd love to hear about it. And watch for updates here. The Poly book will just slowly be getting filled in. We're probably going to have a Polynomial Functors workshop in March. And we'll advertise that on the Topos channel. And yeah, thanks a lot for everything. It's been great having an audience. So yeah, thanks. Okay. Is it still on or is it off?
Still on. Let's see. Nick is commenting. Yeah, like that if we can model dynamical systems as co-algorithms like this, then maybe we can have systems read from databases.
I would love to see, so the question was, if we model dynamical systems like this, potentially we could have them read from databases. And what is weird to me is that it seems that whereas so people talk about branching in quantum mechanics or something. I don't really know anything about what I'm about to say, but world futures that do not, you have some tree, right? Remember the co-free comonoid stuff? You have these, you land in a position, and every position has some number of directions, and for each one of them you pick another position, blah, blah, blah. And we like to think, oh, the universe picks a direction, and then we move that way. But when you get into the database stuff, unless there's some kind of like backtracking search thing that I'm probably misusing the term, it just seems that you don't like pick a direction to move, you pick all of them at once. And it reminds me of this like many worlds or something where like your future is not just the one thing that you get into your eyes, but in some sense, weirdly, if you're going to use this in a databasey kind of way, it seems like it's actually the p bracket I thing is that set of directions here. And yet it is also the query. And so we would not want to separate it and just say, what is your edge? What is your vertex? I mean, you can read it that way, but in some sense, if you want to read it as a data migration functor, then your dynamics is not to choose a direction, but to do all of them and the ways they all kind of cohere as a C instance. So I was really hoping when I first started all this stuff, and I still have a tiny bit of hope just because Poly constantly surprises me, that we could do something like you're saying, and that the database would be read by the dynamical system. And maybe that's true, but that still has to be demonstrated, I think. It's not obviously true, and the thing that is obviously true doesn't quite do that. So let's call that a not very hopeful but exciting possibility. It would be great if there was something else. Just like I didn't know how to find functors for a long time and then found them as path algebras, there may be some like special way you can get it in there and find it. So maybe we can hope for that.
I have a question.
Yeah.
So in a different vein of your work, we've talked about how like having attributes can be modeled using profunctors, bimodules. And here you're using bicomodules.
Okay,
Yeah.
You're back? Okay. So the question was that in other parts of my previous work, I modeled database, the types part, as, whereas here they were living as like a comodule. And before we did them as like a bimodule. And like, in fact, it was like in this paper called Algebraic Databases, with Christina Basilicopoulou and Patrick Schultz, algebraic databases. It was like, I don't remember exactly, but it would be something like a profunctor from C to like T, where T was equipped with a monad structure, like was equipped with like a Levier theory or something like that. And I'm hoping that that could also work, and that it would just be that like we're supposed to work. I have not worked this out. I would like to if anyone or Evan or anyone else is interested, but that this would be something like working in the virtual equipment of monads in cat sharp or something. Like we could still do it, and it would still be like entirely like within this world, and be as general where you have a Levier theory here and not just some like sets. But I haven't worked it out enough. Yeah, thanks.
Nick has one more question. Is there a way we can nest databases inside each other? For example, a binary string / stream can be encoded as a dynamical system. Can we put a bunch of binary strings inside a database?
Okay, so the question is, can we nest databases inside each other? Can we put, like if we had streams as picoalgebras for something, could we somehow use those as the data types or something like that? I would say they're like, you are getting at the, like, in Poly, there's like Poly. It's just a sum of y to the n's. Then there's like, oh, and dynamical systems, and composition product, and this, and comonoids are categories, and bimodules are data migration functors, and there's just a million things to study. And I think, Nick, at this point, you're getting to the point where the world is wide open, and you can ask these questions and pursue them. And it may be the case. I don't know, and it's a great question. You might be able to use kind of this structure where like one database is kind of inside another using a cofunctor. But I don't know. It doesn't sound exactly like what you're looking for there. So, by the way, given any C to C P thing, just like we did before where we had y to y, remember polynomials are just maps y to y by comodules there. For any P from C to C, you can get a co-free comonoid on P. You get it in exactly the same way as we did before. And it will give us some new category called like co-free sub C of P and a cofunctor down to C. And so not much new is there, but the point is like data migration and categories kind of come together in a certain way, and I'm not sure if I'm answering your question at all, but like there's plenty of ways to look into this and see for yourself whether you can do it. But thanks for the question. Okay, should we call it a day?
Yeah.
Okay, thanks everyone.